All right, hello again. I'm Henry. Welcome back. I'm going to be talking about the next little project I did. This little project was sort of one of the classes I took in the winter was called astrobiology, and we looked at the habitability percentages of different planets, what's required to make a habitable zone. And one of the things that was really interesting was this NAAP program, which would tell us the sort of how likely you are to have an extinction event and how likely you are to have enough heavy metals to make a planet based on where you are in the Milky Way. I'll show you that here. Yep, that's the button. So it's this guy, which you can see. I'm going to just get rid of that. But it has these cool little slopes to it. And as you move these back and forth, you can see how likely you are to have an extinction event and how likely you are to have enough metals, heavy metals, to make a planet. And here's where we are, where the sun is. So this was sort of what I went in with, and I wanted to create a program that would be able to take an image with a point on it, a pixel or something, and we could say that's where we're looking at, and I want to know what the sort of chance is that we would both have enough metals and not be exploded from an extinction event. So that's what this code did. The first thing was sort of creating a slope for those graphs that I just displayed. I actually did that later in the code just because it made more sense to get everything all in groups, for me at least. But the way that I wrote those is the heavy element is just with 100 percentage, since it was in a, here I'll go back to that other thing, but it was a split in KPC where it maxed out and died around 25. I had to sort of smudge the numbers a bit because there weren't any exact numbers here, but I went down and said that it went to 0 at 25, and then I said it leveled out right around here, and it had a slope, and this is 100% and this is 100% and stuff like that. So I just used those sort of guesses to create a mathematical model for that, which I described in these equations, where I just have an exponential and I have just a linear equation. Now the real tricky thing was getting an image and turning it into points, so I could get the distance from those points. What I first did is I created an image with the Milky Way, which I can actually show you here. Oops, not that. This one. It's just the Milky Way. It's black and white, and it has 2 dots on it. Actually, no, this isn't the one I want. Here it is. But it has a dot here in the center, one red single pixel, and all the way at the bottom, I don't even know if you can see it, but in this bottom corner is a blue pixel. So I know definitively where there are 2 pixels. I know where there's a red pixel and I know where there's a blue pixel. And I can find those by knowing where those points are. So I'm able to store that data at those points. Now, because everything is being done in pixels, I need to create a multiplier to get everything from pixels into KPC. Since my image, the Milky Way image like this, is the Milky Way itself is 575 pixels. The image itself is 590 pixels. So I needed to convert 575 pixels, which is the size of the Milky Way in this image, to KPC. And going off of this, the Milky Way is about 25 KPC. Because that's where it died. So that was sort of the leaps and bounds I'm making. They're not the most accurate, but they work for this. So that was the leap I made, and that's why I have this pixel multiplier. Now, I want to look at an image that I actually care about, and there were sort of 3 that I created. I have just a pixel here in the middle, that red dot, again, that's our center, and then a blue dot, just off somewhere. This one is having it sort of far away, not too far. This one is having it up here and up to the right, and this one is having it way down here, near the pretty much edge. This was just to test the limits of it. You'll notice in this one and the previous one, I added green borders. That's to give the user an idea of how far you can move a pixel out. Once you move past this green border or into the green border, the program sort of blows up because you're reaching over the 575 pixel limit. So as long as you don't go into the green border, it will still do all the proper calculations and it won't break. The reason I don't have it in this first one is because it was a test run. But this green border was for anyone who wanted to use it. As long as you do not go into that green border, you'll be able to have the program run for you. So with that, I then have something to compare it to from that red and white dot, or red and blue dots from before, I then want to go through every single pixel. This is the process that I thought of and sort of worked out best for me to go through and find where that blue dot is. So I go through, since I know the size of this image is 590 pixels by 590 pixels, if I take the square root of the length of the image data is 590 squared. If I get the square root, I get the length of the side. That only works because this image is a square. This strategy to get the sides would not work if the image was a square, but I did it this way just in case I upscaled the picture to be, I don't know, 1,000 by 1,000 pixels. So this will only work for a square picture. Again, few leaps and bounds being made, but it's working for the sake of this. So then I go through every single pixel and I check the color of that. If that color is equal to the blue, which I got before from the template where I know where blue is, then it will give me my X and Y value, which is pixel values. These aren't genuine X and Y values, but they're pixel values. So I can then use the math.hypot and take it from 295. I know 295 is the center where the red is because this is a 590 by 590 image. So I know 295 will always 100% be in the middle. So if I just treat X and Y as X and Y, and I treat 295 in each direction as X and Y, I can get the X and Y values from the center. Whether these X and Y values are negative, positive, doesn't matter because we're just looking for the distance between the 2 points. I then add in that pixel multiplier and I can get the distance in kpc from the center of the Milky Way or from the center of the image. I then use those equations that I was talking about to apply that distance from the center, plug it into that equation, and I get a percentage of how likely I am to either blow up or have enough heavy elements to make a planet. That's where this comes in. The reason I have 100 minus the extinction event is the extinction event is how likely we are to have an extinction event. So if I want to know how likely we are to survive, I want to look at 100 minus that. So at the center of the Milky Way, my extinction event would be 100%. So 100 minus 100 is 0, 0% of survival at the center of the Milky Way. There's a black hole there. It'd be a real struggle to survive through that. But then as I get farther out, say I have a 50% chance of an extinction event, I would then have a 50% chance of survival. I then multiply those out to get the chance of surviving. And I can check this. I currently am looking at Check Me 2, which is this image, where I have the blue dot up and above. You can sort of get a gist of how far that is. If you know the entire radius here is 25 kpc, you can make some leaps and bounds. But if you run it, you'll know that we have a 27% chance of not blowing up and having enough heavy metals. If I want to look at that original one, where, to show you again, I have the blue dot pretty much directly below the red dot and off to a little. If I run that, I find I have a 48% chance. And finally, if I look at the very edge with Check Me 3, which is this one where I have it all the way down here, pretty much here at the border, I can run that and I have a very low chance of surviving, or of having enough heavy metals, which is the issue here. The issue as you get closer is exploding, of course, and the issue as you get further is you don't have enough heavy metals. So that was the little project that I just worked on and wanted to share with you. The thought process behind this was I wanted to practice taking image data, like looking at an image and sort of taking some data from it. This style of looking for certain colors worked really well for this, but that's because I'm only looking at a single point. To make that single point, I'm in a website called Photopea, which is just a free Photoshop pretty much, but you have to go in and you have to do it single pixel by single pixel. You have to do 1 pixel. Which when you zoom out doesn't look like very much. But if you do not do that 1 pixel, it will only read the first pixel that shows up. So it has to be a single pixel. You can't go something like this because it'll get all confused and it won't know what that sort of pixel that you actually care about is. So that's it. If you have any questions, comments, or concerns, if you want to know what my favorite color is or whatever, please leave them in the comments. Please feel free to check out some of the other videos where I talk about my code or my source presentation. And thanks for your time. Bye.